Jeff and Haruko are on. Yeah.
Well, let's get started then. Thank you, everybody, for coming to Alex Miltenberger's PhD defense. He did his bachelor's in applied geophysics, and what interested me in his application was he had this expertise in geophysics, but also in geostatistics. He had done research in multi-point geostatistics during his undergrad. That's what attracted me. He has been here for about 5 years, and over the 5 years, he has done a lot of work that we'll be presenting today. He has collaborated with multiple groups, with Haruko at Berkeley National Labs, and also he has already 4 peer-reviewed papers. He also won the DOE graduate scholarship, and that allowed him to spend some time at Berkeley National Labs. So, with that introduction, I'll hand it over to Alex, and let's see what he has to show.
Thank you. Thanks for the introduction, Pan. And so, yeah, I have a lot of things to go through today. Like Tapan said, there's been a lot of work that's been done over the past 5 years. And so this is the title of my dissertation. There's a lot of jargon in here. And so I don't really expect anyone to understand what any of this stuff means. It's more so just the purposes for the dissertation itself. So for the purposes of today, I came up with this alternate title that's a little bit easier to understand. So everything we're going to talk about today is with the purpose of being able to measure things that are underground. So, you know, jargon and things with probability and different types of geophysics. But at the end of the day, what we're trying to do is we're trying to understand things that are below our feet that we can't see with our eyes and that we can't touch with our hands, things that we have to like sense with different types of signals like waves and other things like that. So to kind of set the stage a little bit, I just want to give a more concrete example to show what I mean. So this is an example of just imagining that we are going to try to understand this groundwater system and in this case in a mountainous watershed. So this is just a cartoon showing a little chunk of a mountainous watershed. So you can see peaks in the middle, and then you have these streams that start to form coming down from the peaks, and then they coalesce eventually into a bigger stream in the middle. And when we're talking about groundwater, what we're really interested in is things like, number one, how does water get into the ground? How does it get into the aquifers? Number two, how does water move through the ground? Number three, how does water interact with the surface? So how does water get from the ground back into the surface, and how does that affect the quantity and quality of water that we can get in rivers and streams and things like that? And then we're also interested in things like if we drill a well, how much water are we going to be able to pull out of that well? And what kind of effect is that well going to have on the surrounding area as well? And so one of the first things we're going to do when we are going to set up a characterization or set up a management program in a new groundwater area. So is the first thing we're going to do is bring in a geologist, and the geologists are going to do a lot of different things. But one of the main things that they're going to do is they're going to collect different types of geological data. So this is an example from a geologist that I got to work with during my PhD, Gary Weissman, some of his work that he did in the early 2000s. And what he did in this specific study was he took a soil map. So that's what you're seeing in the top figure, and just colored the soil map by different types of soils, different classes of soils. And so by coloring this area with different classes of soils, he's able to show, oh, we have this incised valley fill in the middle here, based on there being a gap between the hatched soils. And so Gary didn't stop there. They actually went out and they drilled wells. And so that's what those 4 dots are. There are 4 different holes that were drilled, and then they logged all of the sediments in there. And so when they logged all the sediments, what they found was that inside this incised valley fill region, we have more sand and we have more cobbles type material. And outside, we don't see as much sand. We see more fines and muds and things like that. And so ultimately, what that's going to help the geologists do, or in this case, Gary do, was come up with this conceptual model for what is controlling the groundwater system, or how the sediment is distributed throughout this area. And so this is just an example of the conceptual model that came out of all of this work, where we have in the far right, the Sierra Nevada mountains, and there's a river that comes out of it into this open basin. And then over millions of years and different glacial cycles, things like that, you've accumulated these stacks of sediment, and through these stacks of sediment, you have these incised valley fill deposits, which are just these big channels that cut through and fill back up with coarse material. And those channels, we think, have a disproportionate impact on the groundwater flow in this specific area. But the high level idea is that the geologist is going to come in and they're going to be able to tell us what's going on here. But when we actually are going to go implement this knowledge in practice and use this to characterize a groundwater system, we need to actually image things in 3 dimensions so that we can get a more specific plan in place. And so that's where the job of the geophysicist comes in, where the geophysicist will come in and say, we're interested in this buried valley. What we know is that in this buried valley, we have a high resistivity, and outside the buried valley, we have a low resistivity. So we can pick out a method to sense that change in resistivity. And so in this case, this is an example. The helicopter is showing an airborne electromagnetic survey, which is where this helicopter dangles this loop and sends out these signals into the ground. And when you send out that signal into the ground, what you're measuring, what comes back from that, looks something like this. So on the x-axis on this plot, we have the time. So we're measuring this signal throughout time as it comes back. And then on the y-axis, we have the change in magnetic field over time. And so it's not super important to know exactly what the change in magnetic field means, but we have 2 input signals here, a high moment and a low moment signal. And then we can record throughout time how those signals decay. And then what's nice is that based on subtle differences in that decay rate, we can infer where we have high resistivities in the subsurface and where we have low resistivities in the subsurface. And so ultimately what we're going to have to do is we're going to have to bring this idea of what the geologist does and what the geophysicist does together. And so to illustrate this, I just want to switch to an example that I got to work on at Lawrence Berkeley Lab, where we were characterizing the geology and the subsurface of this mountainous watershed. So this is in Colorado. And so you can see that the dark colors in the background are just a geologic map. And we have a digital elevation model that we use to kind of add in topography here. And so each of these lines represents where a helicopter flew over and did one of these soundings. And so essentially what you're doing is you're going through and you collect the sounding, and then you do it over and over and over again. And then using some fancy math and some computational algorithms, we can turn those signals into a map of the resistivity underground. And so that's what you're seeing here. The colors are resistivity. And so what's really interesting is then we can't just stop here. This is nice, but it doesn't tell us anything about characterization of the subsurface for groundwater. So this is where we have to bring in the geologist. And so one of the things that we'll do in practice is we'll take this subsurface map here and we will kind of draw lines on it to pull out the main features. So this is just an example of an interpretation that we did where we were able to identify different classes of surface deposits. So like slump blocks and earth flows in this electrically conductive area in the dark blue. We said that this is because there are these blocks of failure where these essentially almost landslides that created this electrical resistivity signature here. The problem with drawing lines on the map like this is that you can give it to another geologist and they can come up with a different interpretation. And so I can't even describe like the magnitude of this problem. This is an enormous problem that affects all areas of earth science, because you give the same data to a different geologist or a different geophysicist, and you get a different answer. And so what we really need to do if we're going to start characterizing things more quantitatively and more rigorously, we're going to need to come up with ways to mitigate or to at least test these interpretations. And so there's a lot of reasons for these multiple interpretations, and it really all comes down to uncertainty. And there's different sources of uncertainty. One of the big sources is just measurement error. Our measurements aren't perfect. They have noise in the systems, and that causes ambiguity when we go to interpret things. We also have non-uniqueness. So this is just baked into the physics of the problem, where two different things in the subsurface can give you the same response. So if you're just looking at the response, you can't tell if it's interpretation A or interpretation B because they give you the same data. And then finally, there's human biases. Like we can just, go into this with the idea of we know what we're looking for, and so therefore we happen to find it. And so this is this conceptual uncertainty with how we think about things, how we think about the interpretation in the first place. And so to illustrate how we're going to approach these problems in this example, or in the rest of this presentation, I just want to focus in on this one area here with that low resistivity. And let's just assume that we come up with an interpretation and we say, this area can be explained by some bedrock system overlaid with this colluvium layer that has something to do with soil development and landslide deposits. And so what we want to do is we want to ask ourselves, is this interpretation consistent with the data? And so we'll frame that as a hypothesis test. The second part is, let's just say we're going to assume that this interpretation is correct and that this is the system that we're going to work with. What we want to do is actually go out and pull some important parameters from that. So for example, the thickness of this deposit here. And there's other parameters that we might care about. We might care about like the shape of the deposit as well. And what we need to do is eventually have some measurement error, or include some measurement error on this these parameters that we're going to try to pull out of the data. And so we're going to frame this problem as an inversion problem. So anytime you see hypothesis testing and inversion, this is what I mean. And the main point of the whole dissertation is that we are going to apply these measure theoretic approaches, which will help us actually address these in a more efficient way than is currently possible. And so when I say measure theory, really all you have to know for the purposes of this talk here is just measure theory is the fundamentals of probability theory. And so that's where this is going to be useful, is because we are going to use these measure theory approaches to derive new probabilistic expressions for both of these two problems here. So that's kind of setting the stage for what we're going to dive into, which is in the real meat of what the contributions are. And so the way that I'm going to kind of frame the rest of this talk here is we're first going to talk about some theory. This is going to be really technical because the contributions are technical in nature. But then what we're going to do is we're going to pull out of that technical explanations of things, and we're going to start bringing an example. So the first example is going to be looking at models for delta sedimentation. And then the second example will be interpreting geophysical data in a mountainous area in terms of to understand fractures and faulting in this region. So what I'm going to start is just with some theory. So we're going to dive into the theory. It's going to get a little bit technical. And before I get too deep, I just want to just highlight that when we talk about uncertainty, the way that we put this into math is using probability. So when we say uncertainty, what we really mean is probability distribution. So just to pull that example from the couple slides ago, let's just assume we have one variable. It's the thickness of this deposit. And what we want to do is we want to define a probability distribution over that thickness. And so what that probability distribution looks like is it's just a curve here. So X is just, it's arbitrary. It's not actually a thickness value, but there's a curve that's over X. And that curve represents the probability of different values that thickness variable could take on. When we expand this into 2 dimensions, that curve turns into a surface. And so we can measure 2 variables, and then that curve becomes a surface, and that's what that probability distribution is. It's the surface. And so when we're working with probabilities in practice, when we bring in geophysical data, our main tool, that's, if you read a lot of the literature in this, the main tool is Bayesian methods. And so what I mean by Bayesian methods is that it's a really high level, almost philosophical concept where you have some prior knowledge, so some prior understanding about what's in the subsurface, and then you have observations or data or measurements. And what you want to do is you want to combine those two things, your knowledge, your theoretical understanding of the Earth, in our case, put that through some belief updating scheme that will combine those sources of information into what's called the posterior state of knowledge, which is just that combines information. And so to add some notation here, D-obs, whenever you see D, think data or measurements. And whenever you see M, think model parameters or variables that we want to measure. And this is Bayes' rule. So this is how we actually do the posterior or the belief updating. And so I'll walk through what each of these terms means. The posterior, you can read this as P of M given D-obs. This is what we want to calculate. We also have the prior, which is the prior knowledge. We have this term up here. This is called the likelihood function. You can read this as P of D-obs given M. And then on the bottom here, we have what's called the marginal likelihood, which you could just read as P of D-obs. And in Bayesian methods, we assume that this is, or this is a constant variable. So usually we don't care too much about the marginal likelihood. Most of the problems with applying this is going to come from the likelihood function here. And one of the reasons for that is when we go take these geophysical measurements, they have sometimes thousands or millions of variables. And so when you have millions of variables in D, your probability distributions get really hard to work with. And so what I mean by that is if you just, to illustrate one aspect of this problem, there's more problems than what I can show here, but one aspect of this problem is that if you just take the single variable example and you just find the average height of this curve, it's about 0.17. Now, if you find the average height of the curve in 2 dimensions, it's about 0.03. And so as we increase this to millions of variables, we're eventually going to get almost 0 everywhere, except for maybe a couple of points where you have this really high localized thing. This is called like the curse of dimensionality and is an enormous problem that makes basically geophysical data really hard to work with in a probabilistic framework. So what we're going to do is we're going to show how to kind of overcome this mathematical limitation of the 0 almost everywhere. And so I don't have time to go into all this measure theory detail. That's all in the dissertation itself. But I will highlight the main tool that we use in measure theory to describe new methods for doing these kinds of problems. And so that tool is called the push forward measure. And so what I'm going to show here is how that push forward measure works. So let's just consider on the bottom, we have a distribution over M. We can call that distribution P prior. And that distribution in this case is uniform. And this black curve here is a forward model that we're going to use to transform this prior distribution into a different space, which will be shown on the right here. So what we do is we run each point in this prior distribution through the forward model, and we get a transformed distribution on the right. And that's called P push. And so anytime you see P push, just think this is a transformed distribution where we know this forward model and we know the distribution beforehand, and we just transform it into a new space. So that concept is going to be really important. And I'm going to just jump right into one of the first main results of this theoretical work that I've done. And so this is going to be an equation that we can use to test hypotheses with high dimensional data. And so this is the equation here. B is what's called the Bayes factor. It's just kind of jargon for saying it's a way to test hypotheses, and I'll show what it means on the next slide. But just note that what we're doing here is we're going to integrate over this data space. This P obs, it represents our distribution of our measurements, so our measurements plus measurement error. P push is our pushed forward prior, so remember that from the last slide, we pushed forward the distribution. And then we have, if we're comparing 2 hypotheses, we'll have 2 pushed forward priors, which is why you see the H1 and the H2. Now, if you go in the literature, what you'll see for this Bayes factor hypothesis testing is something that looks like this. And so again, B is the Bayes factor. The equation looks really similar, but there's a few key differences. Number one is we're integrating in this Bayesian approach over the model space, over M. We have our likelihood distribution, which is essentially playing the same role as our measurement distribution in the measure approach. And then our prior, in this case, is over M, and it's not pushed forward. So what I really want to do is just show intuitively what this Bayes factor is telling us. So to do that, I'm just going to set up a really simple example. Here we want to calculate the Bayes factor of any hypothesis H with respect to a null hypothesis H naught. And that null hypothesis we'll assume is a uniform distribution. And we can use that uniform distribution to simplify the equation from the last slide. This K here is a constant, but this equation isn't that important. What's important is the physical intuition behind what this is telling you. So in this example, the x-axis and y-axis are just two dimensions of our data. And then the blue circles represent the distribution corresponding to our pushed forward prior. And then the black represents the measurement error distribution. And so when you have overlap between your model and your data, you get a Bayes factor greater than 1. When you have partial overlap, you get a Bayes factor roughly equal to 1. And when you have a Bayes factor, or when you have no overlap, you get a Bayes factor less than 1. So what we can do is we can apply this equation and we can simplify these two hypotheses into one number that tells us if it's greater than 1, then it's a good hypothesis. If it's less than 1, then it's a bad hypothesis. Okay, so we'll come back to the hypothesis testing later on in the presentation, but I first want to introduce the second main result of this chapter, where we actually talk about doing inverse problems. And so this is the equation that comes if you take this measure theoretic approach, and I'll just walk through the terms again. This is our measurement distribution P obs. Our prior is here, and then on the bottom here, this is the pushed forward prior. And then the G just represents we evaluated it at the forward model data, but that's just a detail. Now, if you look at Bayes rule, this is the standard. Again, if you look in the literature, this is what you'll see the vast majority of the time. This is the likelihood function. This is the prior, and this is the marginal likelihood. We've seen this before. The important difference between the two equations is that bottom term. So instead of the marginal likelihood being constant, when we use the measure theory approach, the pushed forward measure is not constant. And this is really important. And I'm going to show why that's important on the next slide here. So we're going to walk through this example. There's going to be many steps to this example, but I'm going to walk through it step by step so that you can really see the difference between these two equations and what it's telling you. So to set up the example, let's just say that we have measurements of electrical conductivity, and we have some measurement error on that conductivity, and we want to use that to figure out what the distribution of resistivity values that we can expect. And so this is a really simple example. It's about as simple as you can get for a Bayesian inference problem because it's one-dimensional and it's got a simple forward model. That forward model is nonlinear. When we plot it in log space, it looks linear, but it's actually not. It actually looks something like this if you plot it in regular Cartesian space. So this is a nonlinear forward model that we can use to transform between resistivity and conductivity. Okay, here are the two equations that I just showed on the last slide. And I'm going to walk through step by step the different terms here. So the prior is the same for both equations, and that's what we're showing here in the red on the bottom. So the prior is over resistivity, electrical resistivity. And if we can right off the bat transform this prior using the push forward measure. When you transform it using this nonlinear forward model, you get this non-uniform distribution over conductivity. Now what we're going to do is we're going to bring in the measurement error. And so if we just assume our measurements say that the distribution of possible electrical conductivities is a uniform distribution which is represented by the black line here, then this is essentially the P obs in the measure theory approach, and it's analogous to the likelihood function in the Bayes rule approach. And so now we're just going to use Bayes rule to calculate the posterior. You have a uniform likelihood and you have a uniform prior. So you get a uniform posterior, which is shown in the magenta on the bottom. Now what we're going to do is we're going to push forward that posterior back into the data space. And so what's happened is this posterior, when you map it back into the data space, it does not match your measurement distribution. So this is really important because what it's saying is that when you use Bayes' rule in this way with a nonlinear forward model, your posterior distribution will not match your measurement error distribution. This is really important, and it's potentially causes issues all over. And what we show in the dissertation is that you can correct for this effect by using what we call a change of measure correction, which is really just, to use a technical term, the Jacobian correction. But when you do that correction, you get this dotted magenta line. And if you push forward that using the forward model, you do recover your black measurement error distribution. However, if you don't want to go through that correction because your Jacobian is hard to calculate or the change of measure is hard to do, you can just use the measure theory approach. And if you do that, you get the black line, which overlaps perfectly with the corrected posterior. And so essentially what this is saying is that the measure theory approach here is going to guarantee that the posterior distribution, when you push forward through your forward model, matches your measurement error distribution. And so we are arguing that that is a desirable thing that we want in our inversion for our measurements, our posterior distribution to represent our measurements. So a couple caveats is that this only becomes a problem if number one, you have a nonlinear forward model, and number two, you have measurement error. So if you have perfect measurements, it's like a delta function, then you don't have to worry about any of this. Also, you will have to worry about this if you start doing transformations with your variables to like reduce dimensions, make things easier to work with. But I'll talk more about that dimension reduction in a second. For now, we have this workflow that you can just use to, to know whether or not your problem should consider the measure theory approach or the Bayes rule approach. So you just ask yourself a few simple questions, go through this workflow and see, does my problem need the measure approach or does it need the Bayes rule approach? Okay, I'm gonna now turn to talking about the push forward or talk about the dimension reduction that I mentioned the last slide. And so what we mean by dimension reduction in this case is there's all sorts of dimension reduction techniques, but we're going to use machine learning as a dimension reduction tool. And this is really going to be powerful because nowadays everyone knows there's machine learning everywhere. You see it on billboards on the highway, like it's everywhere. And so people know how to use it, and it can be really powerful for a lot of problems, but putting it into uncertainty quantification can be a challenge. So what we show is if you just use this push forward inversion approach, this measure theoretic approach, you can just rewrite your equation very slightly by using, by kind of wrapping your G of M with this summary statistic function. So essentially, you'll put your data through a machine learning model to reduce the dimensions, and that will make your uncertainty quantification easier. And so there's a couple of things that happen when you do this. Is number one, you risk losing information if you have a bad machine learning model, or even sometimes if you have a good machine learning model. You're going to overestimate uncertainty. That's a risk. If that's important to not overestimate uncertainty, be careful. You also run the risk of biasing the posterior if you have a biased machine learning model as well. So you can't just plug in any machine learning model. It might not give you an accurate posterior distribution. Okay, so there we go. We've made it through all of the theory stuff. And now it's just going to be examples from here on out. So I'm just going to use the simple example here to illustrate the power of this inversion approach and some of the characteristics that happen when you use it. So we're just going to use this really simple example to illustrate. We have a 1D Earth model. The Earth model has a homogeneous background material with just one layer in the middle of it. The layer has a depth h and a thickness delta h. The layer properties, you need two variables to characterize the seismic impedance, which we'll use to simulate the seismic trace for this example. You need the velocity and the density of the material. That's what the rho and the v are. And you have different properties in the different layers. And then we're going to use a seismic source. It could be a hammer or TNT, whatever you want. And that's going to have a wavelet frequency of about 50 hertz. And so because this is an uncertainty quantification problem, we're going to have to define prior distributions over all of these parameters. So that's what you're seeing here. We have our 6 parameters, and then the prior distributions are all uniform. And then we also are going to pick one value out as a true value, and we'll show what happens if we know the truth, how accurate is this inversion approach. And so what we do is once we've done all of our definitions, which you just showed on the last slide, we can simulate 10,000 seismic traces. So these are our seismic traces. This is our true example, and then 3 other random examples. The x-axis is the amplitude, so the seismic amplitude, the magnitude of the vibration. Y-axis is two-way travel time. You can think of that as essentially depth, but not quite. And then you can just see some of the variability that we get in the seismic traces. And so what we want to do is we want to invert the true seismic example for the parameters and with distributions on those parameters. So what we do is we'll use a convolutional neural network. This is the architecture of the network. I have to credit my colleague Xiaowan, who helped me build this. And what you do is you take your input waveform that looks like that seismic trace. We have a couple convolutional layers with different filter sizes. Eventually that turns into fully connected layers, and then we use some Monte Carlo dropout to regularize it. And at the end of the day, what we get is our predicted set of 6 parameters. And so that doesn't give us uncertainty. What will give us uncertainty is the error in this distribution here, or in the error in the machine learning model. So when we apply it to our data, we get something that looks like this. So there's 6 plots here. Those are our 6 different parameters. The x-axis is the neural network predictions. The y-axis is the true variable that we know beforehand. And so these are all the blue dots are each realization in the test set. So we don't have a training set in here. The blue diagonal line is it would be perfect one-to-one predictions. And then the other lines on here are come from the true data. So the red horizontal line, that's our true value that we use to simulate the data, which you can see on the far right. And then the black horizontal line comes from the seismic trace put through the neural network to predict the parameter. And so what we'll do is once we have this, we're pretty much done, and I'll show how this equation applies to these prediction plots here. So if we just look at the y-axis we'll use to get our p prior. The x-axis we'll use to get our pushed forward prior. And then using the uncertainty on the vertical black line, we'll get our observed distribution when it's transformed into this low dimensional neural network prediction space. And so when we do all of that, what we can do is we can get weights for all of our posteriors or for all of our realizations, and those are posterior weights, and we can get a posterior distribution. So that's what we're showing here. The diagonals are the marginal posteriors, where the black line is the prior, the bars are the posterior, and the vertical dashed lines is the true value. So what you want is you want the true value to be mostly or close to where the tall bars are, essentially. The off diagonal elements are correlations. And so the colors represent the normalized probability density. So blues are high probability densities and whites means very low probability of this being the parameter. And what the stars, again, the true variable. So essentially the true variable or the true value is within the posterior for all of our variables, even in the joint space. And so that's what we want. Last thing I'll show on this example is we can see the uncertainty over estimation when we use this method. And so this is what I mentioned when I introduced this, is that when we use this machine learning as a summary statistic, we're going to overestimate uncertainty. And what that overestimation of uncertainty looks like is something like this. So there's 3 examples here. Each example is with a different set of true variables or true parameters that are used to simulate the data. The black horizontal or vertical trace is the simulated data from that true set of parameters. The light gray outline is all of our prior realizations, and the dark gray is the 25 prior realizations with the highest posterior weights. But essentially what you want is, if you have a perfect uncertainty quantification, the dark gray and the black will overlap completely together. So because they don't overlap, what we conclude is that we're overestimating uncertainty. And so this is how you can see if you're overestimating uncertainty. And what's actually interesting is there might be future ways to use this mismatch between the posterior uncertainty and the measured uncertainty to design better posterior estimations. But that's more of a future work thing. For now, I'm just going to wrap up this chapter here. There's a lot of information there, but essentially, we have new equations to do these hypothesis testing and inversion problems. You follow this workflow if you want to know whether this equation could help or not. And then there's a lot of things I don't have time to cover here. I really wish I did, but it'd probably take me like a whole quarter of a class to go through all of this stuff. So for now, I'm just going to move on to the next chapter. So this is where we're going to start seeing the power of these kinds of approaches. So this is going to illustrate how we use the Bayes factor for hypothesis testing. And what we're going to do is we're going to use this hypothesis testing approach to actually test numerical models that simulate how deltas form. So this is just 30 years of satellite data showing the evolution of two deltas in the coast of Louisiana. And so scientists have spent so much time trying to understand how these deltas evolve throughout time. And they're starting to develop these really cool models. But this is kind of an open question of how useful or how predictive these models actually are of delta behavior. And so this work was published in Mathematical Geosciences. You can see that citation down there. But to illustrate what we're going to do a little bit more concretely, essentially what we're going to do is we're going to take this delta RCM model and we're going to compare it to data from a laboratory experiment or a Flume experiment. So in this model, what you're seeing, this is a synthetic delta that was simulated numerically. What's going on is there's a river that enters the ocean here. And then when that river enters the ocean, it's carrying sediment, and that sediment gets deposited. And as that sediment gets deposited, you have this migration of the channels, and it eventually creates this nice, smooth, semicircular shape, at least in this synthetic example here. And so what we're going to do is we're going to try to compare that to a Flume experiment. And so this is in the lab. So it's literally like a tank that they put in the lab. And then down at the bottom here, they put water and sediment into it. And then they just let it go for 53 days or so. And they just watch what happens to the delta. And there's so much data that comes from that. They're taking camera images and laser scans. And what they essentially are going to do is they're going to use that data to study really quantitatively what happens with this delta throughout time. And so what we're going to do is we're going to say, can this model, because it's hard to do this in the field, can this model simulate the Flume experiment data? And what we're really interested in is the channel shape and the channel fluctuation throughout time. And so what we're going to end up showing is that the answer is no. There's some real differences between what delta RCM is able to do and what we see in the laboratory experiment. And so to illustrate that, we're going to use this Monte Carlo approach, where we actually have to, because there's a bunch of parameters that we don't have constrained, we have to simulate a bunch of different examples to see what set of parameters can be even the closest. And so that's what we're kind of showing here is we set up this delta RCM model to mimic the Flume experiment. And we used 673 because we had some issues with the model crashing. But to get those 673 realizations, what we did is we defined uncertainties on all of these parameters. So this is where you start to see the challenge of using these models in practice to actually predict things, is you have things like these smoothing parameters at the bottom that don't have too much physical meaning, but are really, really important for making your model not crash and making it actually work, right? So when we go to use this to predict things, it's going to be hard to say what alpha or what smoothing parameters do I use. So to compensate for that, we have to define uncertainties on everything, and that's why we simulate 673 realizations. And so Next, this is kind of a detail, but what we need to do is we need to quantify the channel network shape. And the way we do that is with these graph-based methods that were developed a few years ago by my colleague at SCRF, Eric Nesvold. But essentially what this is doing is what we're going to do is we're going to take our model at each time step, and we're going to extract the channel network from that model. It's just a binary channel, yes or no, created into a map. And then we're going to fit a graph using what's called the mapper algorithm. And graphs, when I say graph, what that really is just a matrix that has nodes and links between the nodes in that matrix. And because it's a matrix, there's some really interesting properties when you take eigenvalues. And one of the important properties of that matrix is the feeder value, which is the first non-zero eigenvalue, or in this case, it's always the second eigenvalue. And it's not really important, like how you get the feeder value for the purposes of this here, but just know that when you see small feeder value, that is when you have your channels connect or more linear, where each node has only a one or two connections. Whereas if you have a large feeder value, then your channels are really interconnected. So each node has many connections. So that's the intuition. And this kind of shows what the channel network, what happens when we fit these graphs over time. So you can see these are 3 examples that we pulled. We did some clustering to kind of classify these 3, or classify all of our realizations into 3 clusters. We called the clusters channelized, intermediate, and connected. The channelized, you can see in a second why we call it channelized, because it develops these nice channels right here. It develops these nice channels for a little bit, and the connected delta never is able to do that. And so it's channelized, but it's not always channelized. It's just more channelized than what we call the connected delta. And then there's just this intermediate example as well that's somewhere in between. And so then to test this feeder value between the Flume experiment and the model, essentially what we do is we fit these graphs to every single time step and every single realization. So again, we have 673 examples. We take each graphs at each time step, compute that feeder value, and then represent that feeder value as a distribution because it's evolves throughout time. So that's what we're showing on the right. And then on the far right, eventually what we're going to do is we're going to apply some dimension reduction techniques so that we can compare the different the model to the Flume experiment. So we also have to do this to our Flume experiment. So this is kind of the same workflow where we extract our channel networks using some computer vision techniques, and then we fit graphs at each time step. We compute the distribution of feeder values. And on the right, this is at the end of the day, this is what you get. You get this graph that kind of follows the channel network as it evolves throughout time. And so what we're able to show by calculating all of these distributions is that there's some differences between the experiment and the observations. So that's what you're seeing here. The x-axis is the feeder value. The y-axis is the cumulative probability. So all of these curves are a different distribution for different realizations. And so we have 673 curves here. The colors represent those clusters that I showed a few slides ago. And what you can see is that the Flume experiment in the black line, it tends to have lower feeder values than what we're observing in the delta RCM model. And then there's also quite a bit of variability. So not only is the delta RCM more channelized at sometimes, but it's also becoming really highly interconnected. It's having these sheet flow types of behaviors as well. And so to actually bring in the hypothesis testing, we can map all of these curves into a low dimensional space using what's called multi-dimensional scaling. So we take each curve, map it into a point in this 2D space here. And then we have our Flume experiment. We do the same with it. And ultimately what we do is we're going to calculate the base factor. And when we calculate the base factor, we get 0.15. And if you remember, that's less than 1. So when that's less than 1, we say there's something going wrong with the model here. So if you think about what we've done, we've taken this really complicated model with all of these different parameters, and we've compared it to another really complicated experiment and mapped all of that down into one single value that tells us, is the model matching the observations in the experiment, or is it not? And in this case, there's some issues. And so these issues actually might have been addressed in some recent updates to the code. That's really cool. But essentially, doing this is going to help us design strategies to improve the model in the future because we know where it's going wrong. So that's our hypothesis testing example. I'm going to bring in the inversion example now to finish it off. This work was also published last year. You can see the citation at the bottom. This work was done at Berkeley Lab, and there's so many awesome people that helped me with this. So yeah, I have to thank everyone who's been a part of that. It's been great to work with them. But to talk about what we're going to actually do in this chapter of the thesis is this was really motivated by the problem of comparing geophysical data to geological maps and to geological cross sections. So what you're seeing at the top here, this was a map or a geological cross section that was created in the 90s. This is from a part in Colorado. I'll show it on the next slide where this was taken. And then the bottom is a electrical resistivity tomography transect over that same cross section. And what you can see here is we have this big dark blue anomaly. That's an electrically conductive anomaly that doesn't have anything on the map that looks like it could correspond to it. And so if you're not familiar with what electrical resistivity tomography looks like, this is just a picture that I pulled from the internet that I thought did a good job of explaining it. You go out with these rods, you stick these rods into the ground along a line, and then you hook these wires up together, and you have a computer put current into two wires or into two rods, and then you measure the current in another two rods, and you do this over and over and over again, and eventually you can use those measurements to infer the resistivity structure below the surface. So a little bit of background about where this comes from before we get into the details of the inversion. This was again in Colorado. If you've heard anything about the Colorado River over the past year or two, you know that there's a big issue with the water levels being super low. So there's a real big need to understand how water gets into these systems and how to manage that properly. So we're working at the very edge, right in the highest mountains of Colorado. And so our study area is here on the right. And there's a few geologic features. You can read the legend if you're interested in them. But a few main points is we have this East River. This is the main river that goes through this watershed. And our study site cuts across this river. And we have this electrical resistivity cross section, which I showed on the last slide. And we also have these boreholes, which are the green diamonds. And so just bringing back that resistivity cross section with the geologic cross section from the last slide, we have two wells, well A and well B, that go through here. And so well A goes through the anomaly, or at least close to the anomaly. Well B is far away from that anomaly. And so what you see in well A is the shale is like crumbly, it's broken, it's highly fractured. And in well B, you have really tight shale. There's barely any fractures except for these vertical ones. And actually they think that those just came from pulling it out and the release of pressure. So we actually think that in the ground that shale, it doesn't even have those those horizontal fractures. But so we interpret this as this anomaly here is being caused by the increased pore space and increased flow that comes from having this really fractured shale in this region. And so our goal is to understand why this is here, because it's not on the geologic map. And there's good reasons for this. I mean, the geologists aren't looking at every little detail. And there's cover, there's soil and stuff. I've been out here, you can't see it. There's nothing obvious from the surface. So it's only when you get the geophysics and actually start investigating the subsurface that you start to see that there's something going on here. And so we think that this has a big issue, big effects on the groundwater in this area because it's so highly fractured. So we really want to understand where that came from. And so what we did is we spent a lot of time digging through the literature. We looked at the geologic history of the area, and we came up with 6 different hypotheses for what could be causing this fracture, or this fracture zone, I should say. The first hypothesis is that something due to the deposition of the sediment, of the shale, caused a layer to be deposited that is more conducive to fracturing for one reason or another. We don't necessarily have a good explanation for that. What the shale would, what about the shale makes it more susceptible to being fractured, but it's possible that something, there's a layer of sediment that follows these bedding planes that's being fractured. So that's one hypothesis. In that case, you have this really shallow dipping. It's almost horizontal, but it's not quite a layer. Our second and third hypotheses are that there's a thrust fault that causes this, because faults are obviously cause fractures in rocks. So there are thrust faults in the area. There's actually a really big thrust fault in the area. So we thought maybe there's another thrust fault that's causing this anomaly. Because we don't really know which way that fault would dip, we just assume it could dip either to the southwest or the northeast. So we get two hypotheses out of there. We have two more hypotheses that are related to the high angle fault, normal or reverse fault. We don't really distinguish in this example. And this was motivated because we do see other faults in the area that are both normal and mostly reverse faults, but we think there could possibly be normal faults as well based on the current stress state. So we divide that into two hypotheses as well, dipping southwest or northeast. And then our last hypothesis is a tension fissure, also known as a Sakung fissure, or actually just Sakung is a German word. And these are seen in the area. These form when the glaciers in this example form from glaciers melting away and releasing the stress that was on the rock. So all that weight from the glacier is gone. The rock expands and rebounds, and when that happens, it cracks and forms these fissures. So this is what we see in other parts of this watershed. And so we also have our final hypothesis that it could be related to that. And so the main thing to note between all of these six hypotheses is that the thing that differentiates them that we can possibly measure is the dip angle. So we think that the bedding plane hypothesis is most likely dipping to the shallow, and then we increase the dip angle down to the tension fissure, which is almost vertical. So if we can just pull out that dip angle, we can start to figure out which of these hypotheses is most consistent with the data. So the way that we do that is we actually create a forward model, or we create a prior model that includes the dip angle. And so we just model this system using this really simple 5-parameter model. The 5 parameters are shown on the top. The phi is the dip angle, and so that's measured from the northeast. The x naught is the position, the center point of this fracture zone. The h is the thickness of the fracture zone, and then the fracture zone has its own resistivity rho f, and then there's a background resistivity rho b. So we are ignoring heterogeneity in here. We show in our paper that the heterogeneity has only a minor effect. Most of the variability is from the fracture itself. And so the bottom here is just 4 different random realizations, subsurface models from using this prior model. So you can see a mixture of dip angles of that fracture zone, of thicknesses of the fracture zone, and of the resistivity contrast between the fracture zone and the background material. Then what we do is we simulate using those models 2,000 sets of electrical resistivity tomography measurements. The measurements kind of look like this. There's no great way to really display the measurements, but we came up with a projection. We projected each point into a space based on the spacing of the nodes, or the soundings, and the position of the soundings. So you can kind of see, roughly the deeper soundings versus the shallower soundings. And then on the right is our observed data. And so what we're interested in doing now is using these data to actually pull out the dip angle. And so to do that, we trained a random forest model so that we can use that as a dimension reduction tool. And so what that random forest model looks like is we input a set of ERT measurements. We run it through 5 different random forest models, which have each been trained on the same data. And then we output a set of model 5 model parameters that we're interested in. And so on the right, we're showing the prediction plots from using this forward model. So the x-axis is the true dip angle, or the true parameter, and the y-axis is the predicted parameter. The diagonal line is the black line that goes diagonal is 1 to 1. The pink dots are the training set. The blue dot or the blue squares are the test set. When we actually go to calculate things, we'll ignore the training set and just use the test set. But we've done this for all 5 of our parameters. And so I showed in the beginning of the presentation how we use this to calculate the posterior. So that's what we're going to do. I'm only going to show the dip angle because that's all we care about. But what we're going to do is we're going to put our measured data through this, and our measurements have error on them. So we're going to put our measured data through this, and we're just going to look at the posterior of the dip angle. And when you do that, you can use this equation that I showed in the beginning to calculate the posterior, and this is what you get. And so the black horizontal line is, the dashed line is the prior, the solid line with the gray shading is the posterior. And what we're going to do now is going to bring in our 6 hypotheses. And so if we just look at the dip angle posterior, which again, our x-axis is the dip angle and the y-axis is the normalized probability density, we'll bring in what we're calling hypothesis likelihoods for each of our 6 hypotheses. So each hypothesis gets its own curve. And the curve is basically saying, if we just take this thrust fault example on the left, this curve is saying, if we have a thrust fault that dips to the northeast, we expect the dip angle to fall within this distribution here. So we've done that for all 6 of our hypotheses. And then essentially by calculating the overlap between each of these hypothesis likelihoods with the dip angle posterior, we can see which hypothesis is most likely. And so we can get probabilities for each of our 6 hypotheses. And so you can see that the 3 on the left have a much lower probability than the 3 on the right. And so essentially, if we just make kind of an arbitrary cutoff at 0.1, we can say that we would reject these 3 hypotheses on the left. And we would say that our most likely hypotheses are these 3 on the right. And so those are the solid lines there. And so if you think about what we've done is we came into this, we had no idea what was causing all these fractures. But the process of going through and quantifying everything and actually testing it against the data has helped us reduce our uncertainty about what the heck's going on here to eliminate some unlikely unlikely causes like this tension fissure. And so now what we can do is if we're interested in focusing on this further, we can go collect data that will look for evidence of faulting or evidence of bedding planes that are fractured. So it's going to give us more insight into what to do to proceed further. And it's also going to tell us that we better be on the lookout for effects on the groundwater system from these faults that we didn't even know existed before this. So I'm going to leave it on this slide, and this is kind of the final slide here, just highlighting that what we've done is we've in this dissertation, the main contributions is just we've shown 2 new equations using this measure theory approach that will help us do hypothesis testing and inversion to understand complicated models with complicated data. So with that, I also have some acknowledgements, but should I just go right into those? Yeah, all right, I'll go right into those. Yeah, so first of all, yeah, I have to thank everyone on my committee here for being here today and just for all the guidance. It's been a long 5 years, especially with the COVID situation covering like half of it. But Tapan gave me a shot. Like I wouldn't be here if Tapan didn't, see my application to give me a chance to come in and show, what I could do. And so thank you for that. And thank you for being there for me over the whole years. I know it wasn't always easy, but it's been great. It's been great to just, work with you and to, have your input every step of the way. Jeff, if you're on Zoom, but thank you, Jeff, for everything. The last year especially has been really, really fun, really digging into the theory. Jeff has like guided me, this started out like, what's going on? Like the Bayes rule example isn't lining up with the intuition. So like, what's going wrong? And so Jeff like kept pointing me into the right direction. And I don't know if Jeff knew exactly where that was going to end up, but he somehow always pointed me into the right direction. And it's just been super fun to be able to dig into some of these things with Jeff. Rosemary, I had a lot of fun working on this Insides Valley project. It's been super cool to like actually, be involved with the planning stages, the whole process. I've learned so much from just being a part of that and seeing you and your group operate. So thank you. Haruko was my advisor at Lawrence Berkeley Lab. And Haruko has also been really awesome. Like, she's been so nice and so supportive, and also like giving me the freedom to explore my own directions, even when it might not have been directly helping her research goals or her research group. She's given me the freedom to actually explore those things. And George, I don't know if George knows this, but George is actually the inspiration for thinking about everything in terms of hypotheses. He gave a talk, a guest lecture at, I forget, it was like quantitative sedimentary processes or something like that. Gave a talk at this and was just talking about these crazy complicated geomorphic models and narrowing everything down into one like testable parameter. And it was so cool. It was like, after that, I was like, oh, light bulb moment. And then we got to work together on some modeling, and it's been really fun as well. So thank you, George. I've had a bunch of other scientific mentors at Stanford and beyond. Here's a few of them. Dusty, I did my second project with him. Jenny was there with me in the beginning, kind of helping me out, and I TA'd a class for her, and she's been really nice and supportive. Matthew, it was really, I don't know if he's on here, but he really was inspiring. I took his class. It was probably my favorite class at Stanford. It was about modeling rivers, and it was so cool. And I just love the way he thinks about problems. Paula, I'll get to Ken in a minute. Paula was at UT Austin. She guided me through this, the process, kind of writing my first paper. And she really didn't have to just take this random kid from Stanford and like help him write a paper when he had no idea what he was doing. But she did, and she was super nice about it and super helpful. So thank you, Paula. Snahamoy was my undergrad advisor, who he didn't even want to hire me at first. He took someone else, and then he had a job posting. I applied, someone else took the job, and then ended up not taking it. So he then brought me on as the second choice, but then it was great. For 2 years, he really helped me understand the multiple point statistics and geostatistics. And then he encouraged me to apply for fellowships, and also just let me, he brought me to Spain to give a talk at a geostatistics conference. And it was just like the coolest thing. I was an undergrad, I had no idea about research, and he just like took me to Spain, let me present at this huge geostatistics conference as like a 19-year-old kid. And it was just, I learned so much from him and his support. I definitely would not be here if it wasn't for him. Ken and Baptiste, they're both from Lawrence Berkeley Lab. These guys are awesome. These guys are so cool. I got to spend like a week with Ken and a week with Baptiste over in Colorado doing some field work, and I see Baptiste at Lawrence Berkeley sometimes too. These guys are so cool. They've just got the really cool work that they're doing, and just also a lot of fun to be with. There's been a couple of important students who have really like helped mentor me through this process of getting the PhD. Vishal is not here. Well, actually, Vishal, Noe, and Noah have all graduated here. Sebastian was a postdoc at Lawrence Berkeley. He's now a research scientist at Lawrence Berkeley. All of these people have actually made like a big difference on helping me get through grad school, understand how grad school works, and then just beyond that as well, even things like talking about what to do next, and what it's like to be a postdoc and things like that. So big thanks to these four people in particular who really mentored me. Oh yeah, I also have we did some field work with Sebastian, and we got to take some pictures of playing with heavy equipment. And so this was a fun day. We got to go out. We have more pictures of swinging a hammer, but he has them. I didn't get them from him, but this is a cool picture of like drilling a well. This thing is actually like 10 feet below the surface, and you're just doing it with your hands. And it was a lot of fun to get out there with Sebastian. Have to thank everyone in SCURF. This is our most recent photo. What a great photo, I have to say. Coolest group ever. Really is the coolest group. The sponsors are amazing. The sponsors just, they contribute, they help you understand problems, they give you the data that you need to work with, and then they give you opportunities to collaborate as well. It's been, yeah, such an awesome group. All the students are like top notch. It's amazing. A lot of friends I have to thank as well. There's just too many people that I've met here at Stanford, and they're all like, seriously, the coolest people at Stanford here, like super smart, super on top of it, and just really motivated, just really fun people to be around. This is just a big list of people that I've met, through Stanford, and so thank you all. You've all, helped me get through this in your own way, and so I really appreciate that. I also have friends outside of Stanford, believe it or not. These people, help me get away from, the hard university life sometimes. And I really appreciate, all these people who have stayed, in contact with me throughout the last 5 years. And it's been fun to get to catch up with them occasionally. And some of them have moved out here too. So it's been really fun. I have to thank my partner, my girlfriend, Audrey, and the Berg family as a whole. We have a few of them here today. I really appreciate you guys coming out here and for really just like bringing me in as like part of the family. It's helped so much to just have like kind of a home away from home. And if you can't tell from all these pictures, we love dogs. We actually got our own pandemic puppy as well. It's kind of crazy, but it's fun. And then lastly, I have to thank my own family as well. These people, my mom, my dad, my brother, my sister, Corey. It's been hard because we haven't, we've been across the country, and I know that's a common thing with, people at Stanford here. We have family all over the place. But it's been hard, but I've appreciated every chance that we've had to get together and actually and just hang out once in a while, and it's been really fun. And they've been with me from the start. Like even I love this picture. It looks like they're locking us in the cage, but we actually just wanted to be in there because we thought it was funny. But yeah, I mean, they've been my whole life. They've been there and been supportive every step of the way, and so just thank you to my family. So with that, I know we're a little bit over time, but I'll just kind of leave it on this technical note here, and happy to take any questions.
So this is the time when the public is invited to ask questions of Alex about anything he presented today. Questions for Alex, either in person or on Zoom. I don't know who's managing the Zoom room.
When you tested that model 673 times, seems like an odd number. Can you go over the reason why it was that number again? Was the model just crashing when you went over?
Yeah.
Tested it more times than that?
Yeah, we ran like 1,200 and like almost half of them crashed. I mean, it was the model, it was just like someone kind of stitched it together for a research project, and then it's since been updated and it's much more stable now, but when we were working with it, it was just crashing all the time. And so that's just the number that we ended up with.
So if you went to 674, it would crash?
Oh, no. Sorry. We could, if we ran like 2,000 times, we might have gotten like 1,200 data points to work with, or 1,200 simulations to work with. But it takes like 2 hours per simulation, so it's really hard to do that like thousands and thousands of times. I mean, it was like a week on the cluster computer.
Got it.
Okay. I'll let George pick people.
I'll ask first. So thank you, Alex, for bringing this measure theory approaches for address an inversion problem. So I was wondering for the push forward density estimation, do you think is there any like challenges in the future that if we use that like for the dimensionality, or if there's any existing challenge we should keep in mind, or when we use that, should we be cautious on anything?
Yeah, one of the hardest things is with this approach is to get maps of the subsurface. So when you have like 1 million pixels that represent like a full 3D gridded subsurface model, that's going to be really, really hard with this, because that, you know, if you have 1 million pixels that you want to calculate the posterior for, you have like 1 million dimensional probability here. And then that's where the real challenge comes back into play of having high dimensional data. So right now, this is only going to be really useful for pulling out maybe up to max 10 parameters. But if you want to start making 3D maps with this kind of inversion approach, it's going to be really hard. So that's a real frontier. I think there's some ways to address that using some like, you know, new kinds of deep learning methods for estimating high dimensional densities. I think that's an exciting front, and it would be really cool to see some of that start happening.
You had the schematic for the workflow. If you have errors, yes or no, for using the measure theoretic versus Bayesian. And maybe I missed it on the right. So first, if you had errors, obviously you would do it, and then nonlinear, then also dimensionality was something. Oh, nonlinear dimension reduction.
Yeah.
So can you talk more
About what nonlinear dimension reduction means?
So if you're using any nonlinear dimension reductions, you would use the measure theoretic approach.
Yes, exactly. Yeah. So you can imagine an example where you have like a linear forward model, but it's high dimensions, and you have no measurement error at all. But if it's high dimensions, it's still hard to work with. That's why a lot of Jeff's work using principal component analysis and multi-dimensional scaling and things like that. If you're going to start applying things like that, even to like simple problems that have linear and models and no data, those transformations, anytime you do a nonlinear transformation on your data, you're going to risk skewing that the probability. You're going to transform the probability density in a way that you don't necessarily know if it's correct or not. So when you're doing anything, even with simple examples where you're transforming things, you're going to need to consider the measure approach.
Great talk, Alex. I'm curious about your hypothesis testing approach with your key example, which is really interesting. You obviously first need some initial inversion to define what hypothesis you're going to test.
Yes.
So do you have any thoughts about how to best make sure you're understanding the uncertainty in that first image that you're using to define your hypothesis to the spectrum of different hypotheses you're going to look at when you're starting with that initial inversion?
It's a really good question. I don't think there's a real solid answer to that. I think that's a little bit subjective to because it is really important to do these inversions first to even come up with your hypotheses in the first place. That inversion is going to tell you some really basic structures like high resistivity, like it's going to take a second, but like high resistivity over here and low resistivity over here. It's going to tell you like that basic thing. But honestly, you could play with that for a while. But I think from a practical standpoint, like if you're trying to get through something fast and you don't have time, you can just kind of do any inversion and you can get some example that you can then like work with to test things more quantitatively. But no, there's definitely a degree of subjectivity to like doing that inversion in the first place. And it's possible if you try new inversions, you'll see different things pop out in the data that you can then investigate more.
Do we have any questions from online?
Check.
Okay.
Okay. Okay, last opportunity. Sure.
So just if you had another year, what would you do?
If I had another year, let me see. I think what would be really, really cool would be to get a neural network that basically is able to just estimate this posterior distribution automatically without having to estimate the top and bottom here individually. So to basically train a neural network that will estimate your posterior distribution exactly. I think that's like kind of the holy grail, because if you can just, because you know, right, you can define like a objective function. If I go back to one of the previous slides, you could define an objective function that says your posterior, the pushed forward posterior needs to match your measurement distribution. And that's a really nicely well-defined objective function. I think you could do something where you use these neural networks to transform the spaces in a way that optimizes the uncertainty or optimizes the posterior distribution so that the black overlaps with the dark gray, essentially. I think that would be really cool if I had another year. But honestly, if I had another year, I'd probably just spend it writing papers because I have so much work that I haven't written.
Great. Well, thank you all for coming. I think we're going to move to a closed session now after maybe a quick break. But let's give Alex a final round of applause for a great job.